We're finally on the last section of this chapter, which is good news because hasn't it seemed like we've been on this chapter since the last ice age? I think so. So remember that this first chapter was supposed to be a lot of review, and it was. Um, there's no other chapter in the book that has 10 whole sections. So what they did was they picked and chose every little individual thing that you're going to need to use throughout this year in pre-calculus, and they jammed it all in chapter 1. And so this section 110, which deals with mathematical modeling and variation in linear regression, it seems kind of out of place, but remember, we're just taking all the stuff that you learned last year, packing it into one chapter so that we can just move forward from here. All right, so the plan is to recognize and apply several different forms of variation, and then also use the regression capabilities of our calculators. And yep, we've done both of these things in Algebra 2. So first of all, what are we talking about when we say variation? A variation is a simple way to generalize a relationship between two or more variables. And there's 4 different types of variation that we are going to be dealing with. The first and easiest is direct variation. And I'm going to go through these one at a time, but I'm just going to bullet point all 4 types right now. Then there's direct variation as a power. There's inverse variation. And lastly, joint variation. So like I said, we're going to go over those one at a time real quick. Direct variation is simply a linear relationship. Rather than saying y equals mx plus b like we used to, we simplify it a bit by just saying y equals kx. And k is a constant. And so that's usually the first thing that you need to do when you're doing work with this, is figure out what that constant of variation is. Some other ways of saying direct variation, you can say y varies directly as x. You can say y is directly proportional to x. And you could just say the equation y equals kx for some non-zero constant k. So if you see any of those 3 wordings, you should know that you're talking about direct variation, just y equals kx. So how do you decide whether or not a relationship varies directly? Well, it's pretty simple. Thinking about what our graph of y equals, in this case, kx is, it's just a linear relationship. It's a straight line. So you're just going to have the same type of increase or decrease for both x and y. So if y increases or decreases by a consistent amount as x increases by a consistent amount, then it's direct variation. Remember that this is a linear relationship, and k actually represents the slope. And so you know that if it's a linear relationship, that the slope is constant. That k value is called the constant of variation or the constant of proportion. Regardless if the relationship is direct or inverse or joint, k is always called the constant of variation. All right, so this is kind of what we're talking about. This here is a scatter plot, represents some unknown set of data. And you can see that it looks like it's consistently going down. As x increases, y goes down by a consistent amount each time. It looks linear. All right, so that's an example of direct variation. All right, in this particular case, the slope is negative, and so we refer to it as having a negative correlation. Here we have another set of data on a scatter plot, and this looks like it's consistently increasing as far as the slope goes. So it has a positive correlation. And then there's this thing, which it's just a big blob of points. It doesn't really look like it forms a line at all. Okay, I would say that there's no relationship between the two of them, between the x and the y. And so you refer to it as having either no correlation or zero correlation. All right, so that's what you need to know about direct variation. Now we're going to do direct variation as an nth power. So instead of just y equals kx, now it is y equals kx to the n. And some ways of saying direct variation as a power of n. Y varies directly as the nth power of x. Y is directly proportional to the nth power of x, or just the equation y equals kx to the n for some non-zero constant k. The next type of variation was inverse. Inverse means that as x increases, y gets closer and closer to 0. And the formula is y equals k over x. You could write it also k times 1 over x. And some ways of saying that are, obviously, y varies inversely as x. Y is inversely proportional to x. Y equals k over x for some non-zero constant k. I think you're kind of getting the idea of different ways of saying things. And the last type of variation that we're dealing with is joint variation. Okay, and that includes all the previous types of variation that we talked about. Direct is a power of n. Inverse, all of those, but now we're using more than one variable. Some ways of saying joint variation. How about z varies jointly as x and y? Yeah, I'm good. How about z is jointly proportional to x and y? Yes. Z equals kxy for some non-zero constant k. Now that isn't the only form that you could have, because you could have inverse variation, and you might have a k times x over y and that type of thing. Okay, so what does this all mean? How do we put this all together? All right, well, we're going to be described a particular model, direct. Direct is a power of x or n, inverse or jointly, and we're going to come up with an equation that relates the two variables. So in other words, to get the ultimate equation, we need to figure out what that constant of variation is, k. So let's try an example. Y varies directly as x. And right there you should know what the formula is that you're going to be using. If y equals 16 as x equals 12, find the model that relates x and y. So all they want is the y equals kx equation, but you have to find k. So right out of the gate, we're told that it's direct variation, which means we use the direct variation model. Y equals kx. Solve for k. And then all we need to do, because all they're asking for is for us to find the model, rewrite the equation with 4/3 in for k. That's the model. That's all there is to it. Sometimes it's a little bit different than this precisely. For example, y varies inversely as x. If y equals 8 when x equals 12, find y when x equals 8. So this is different. They're not asking us for a model here. So what's the deal? How are we supposed to figure out what y is if we don't even know what k is? Well, we can figure out k based on that first information, and then we can use that to figure out what y is when x equals 8. So we're doing the exact same thing that we did in the previous example. We're just taking it one more step. All right, so what do we got here? We got y varies inversely, which is y equals k over x. We need to solve for k. And then we need to rewrite the equation with that value of k in it. So y equals 96 over x. Okay, that is our model. That's not what they're asking for, but we needed the model in order to do the next part, which is figure out what y is if x equals 8. All right, so here we go. We have y equals 96 over x, and if I plug 8 in for x, I am going to get y equals 12. Let's try one more example. We're going to do a joint variation 1. And it's a lot easier if you dissect the information that they give you one word at a time. For example, y varies. And there's going to be a k in every variation equation that we do. So let's just put it in right away. Jointly, which means there's more than one variable coming, as the square of x, and they didn't say inverse on that, so we can assume that it's direct, and inversely with w. So the inverse is just for the w. That is the model for this particular variation. Y equals kx squared over w. And we do know what y, x, and w are, so we're going to solve for k first. Okay, as soon as we know k, we know what the model is. It's the only thing that we don't have on there. So start plugging those values in. Okay, 16 over 8 is 2, and 26 divided by 2 is 13. So we have our model. All we're going to do is go to that first equation and replace the k with 13. All right, that is all there is to figuring out these variation equations.